All right, so hello. Today let's talk about infinite limits. Infinite limits is actually used when we solve for the limits of a specific rational functions. So if you can recall, this is a graph of a rational function. A rational function y is equal to 1 over x. So if you will be solving for the limit of functions like this, it is best applicable if ever you will be utilizing the theorems involving infinite limits. So let's, for example, in this specific problem, if you notice, if we solve for the limit of f of x as x approaches 0 from the right, so if you'll be solving this, it will be a lot easier, right? Because you will be, or you're provided with a graph. So technically, you can just use inspection in solving for the limit of this specific function. So if ever we will be solving this, so limit of f of x as x approaches 0 from the right. So it's 0 from the right. So technically the answer for this, so from the right, 0. So it will be positive infinity. All right. So how about we'll have another limit. So assuming we have this other graph, so this is a complicated rational function. So just want to tell you though that this is the equation of that specific rational function graph. So say for example, you're asked to solve for the limit of f of x as x approaches 2 from the right. So this will be the 2 and coming from the right, so starts here. And if you solve that one going down, so I believe you'll agree with me that the answer for that is it approaches to negative infinity. Okay, so that's how we solve limits of infinite, or solve for the limits of rational functions in infinite limits. So let's try to have another given. For example, we have this limit of f of x as x approaches negative 3 from the right. So it will be negative 3 from the right. So if we trace it, it goes up, up, and up. So technically, the answer for that is equal to positive infinity. So if you notice, if you notice with all the answers we actually have an answer of positive infinity or negative infinity. Yes, if ever we'll be doing infinite limits, we will actually be getting answers like these two. It could either be positive or infinity or negative infinity. However, I just want to emphasize here that when we say positive infinity and negative infinity, that does not mean that this is a number. That does not mean that the limit does exist. I just want to clarify that even if your answers are these answers still represent that the limit does not exist. It is just that we use positive infinity and negative infinity to denote and to emphasize that the numbers you're having is increasing rapidly if it is positive infinity. So it just simply denotes, or it just simply denotes that, yeah, it just simply denotes that the answer, as it is approaching to that specific number, is increasing. And on the other hand, if you have negative infinity, that simply means that your answers, or yeah, the answers for your y decreases indefinitely. So I just want to clarify that when we have answers like this, still the limit does not exist. However, these were just used to represent whether your answers is increasing indefinitely or if it is decreasing indefinitely. But the challenge here is, what if you are not provided with graphs? What if you're provided with functions? What if you're provided with equation and you will be asking to solve for the infinite limit of that specific function? Of course, it takes time to graph that equation and then solve for the limit, because as we all know, it will be a lot easier if the graph is provided. But what if it is not provided? So that is why, or here comes the theorems that we need to apply in solving for infinite limits of rational function. So these are the theorems that we need to familiarize. So let's have this one. So let R be any positive integer So the limit of 1 over x to the power of r as x approaches 0 from the right is equal to positive infinity. So please always remember that. I just want to emphasize here that it does not always mean that your x is always approaching to 0, okay, or 0 from the right. What it is actually is emphasizing here is x is approaching to a number where your denominator be 0, or x is approaching to a number where we are approaching to a number of your vertical asymptotes. Well, I'll emphasize that one later on. So this is the first theorem under infinite limits. The second theorem is here. So if a limit of 1 over x to the power of r, if x as x approaches 0 from the left, so it will be positive infinity. Okay, the answer will be positive infinity if our r, which is the exponent of the rational function, is an even number. And limit of 1 over x to the power of r as x approaches 0 from the left is equal to negative infinity if our r, which is the exponent, is an odd number. So always remember that. So technically, when solving problems like this, it will be a lot. It is very easy to solve problems when you are having this format, because there are nothing, or there are no things that you will be considering. It will always be equal to a positive infinity. Whereas if it is 0 coming from the left, so you need to consider the exponent, whether if the exponent is even or odd. So familiarize this, because you will be applying these concepts from our theorem in solving for infinite limits. So let's have our first example here. So limit of 1 over v squared minus 25 as x approaches 5 from the right. So as I've mentioned earlier, as what I've told you, it does not always mean that our variable is approaching to 0. Okay, that's what I've mentioned. It will be approaching to where, or it will be approaching to the vertical asymptote. It will be approaching to where your, or to that value where your denominator will be equal to 0. Okay, so because technically, as mentioned, it does not exist. It is just that we are using values of we are just using values to represent that specific answer. So if ever we'll be solving this, so limit of 1 over v squared minus 25 as v approaches 5 from the right. So if you substitute, if you do manual substitution, if we substitute 5, I believe it will be equal to undefined. So that's why the answer is actually does not exist, or DNE. But again, as what I've told you, instead of writing DNE, we will be representing it whether it is positive infinity or negative infinity. So to solve this, let's try to apply. If you can remember from the theorem, from the previous theorem, from the right and from the left, if you can remember, if it is from the right, it will be automatically equal to positive infinity. As I've mentioned, it will be very strict when your number is approaching to a coming from the left, because you'll be considering the exponent of the denominator. But for this, since it is coming from the right, then without any further analyzation, the answer will always be equal to positive infinity. You can scan over the theorem flashed earlier, and you will be able to see on the first one that limit of 1 over x to the power of r as x approaches 0 from the right, will always be equal to positive infinity. So again, the answer for this problem, or for this limit, is equal to positive infinity. So meaning values um, values of y as your v is approaching to 5 from the right is increasing indefinitely. All right, so let's proceed to another example. What if you are asked to solve this one? So one limit of 1 over v minus 5 as v approaches 5 from the left. So as mentioned, this is the tricky part. Why? Because this time we are approaching from the left. Okay, we are approaching from the left, where unlike with the previous example, we are approaching from the right, so it will be automatically positive infinity. But for this, 5 is now approaching from the left. So if it is from 5 from the left, we will always remember that if it is 5 from the left, we will always remember the r. If you can remember, r is the exponent. Okay, so if you can remember, if r is even and if r is odd, and let's try to recall. And you can scan over your notes. If r is an even number, then the answer is positive infinity. And if r is an odd number, then it is negative infinity. So let's try to analyze this specific example. So limit of 1 over v minus 5 as v approaches to 5 from the left. So, okay, it's from the left and v minus 5. So technically, if ever we'll be evaluating this, it will be like this, 5 from the left and 1 all over, and v minus 5 is just v minus 5, and there is an imaginary 1 exponent there. So understandable that there is 1. So our r here is equal to 1. And since 1 is an odd number, so since 1 is an odd number, coming from the theorem that if r is odd, our answer will be equal to negative infinity. So that's the reason why for the second example, the answer is negative infinity. All right, let me proceed to another example, still under infinite limits. And we have limit of 2 all over s squared minus 4 to the power of 4 as s approaching to square root of 2. All right. So if ever we'll be solving this, um, we can try to analyze first, because as what I've told you, we need to double check if it will be a problem in the denominator. Technically, if you are provided with a problem like this, if you will be looking at it, square root of 2, if we substitute that, it will not be 0. So if we solve this one, it will just be s squared, so square root of 2 squared minus 4 to the power of 4, because again s is equal to square root of 2. And if we simplify that, it will be 2 all over, we can cancel, and that will be equal to 2 minus 4 to the power of 4. And so it's 2 all over 2 minus 4 is negative 2 to the power of 4. And negative 2 to the power of 4 is equal to positive 16. So the answer is equal to 1 over 8. So please be careful, okay? Well, it's not intentional though, but if you will be looking at it, there might be some problems wherein, if you notice, if we try to substitute it, it will not be equal to 0. Again, infinite limits is only applicable if your answer will be DNE, or if your answer will be does not exist, or if your expression will be having a 0 denominator because it will be undefined. However, do not be confused. Do not automatically conclude that if it is in this format like this, you'll automatically say that it is for infinite limits, because there might be some times wherein the problem seems to be like that. However, it it can be solved the other way around. So that is why, especially in dealing with limits, you need to be very extra careful. Okay. Yeah, to be very careful in solving for limits, because as an example like this, if you notice, it will not make the denominator 0. So again, be careful if you will be solving limits. All right, so let's proceed to another example. And I believe this will be the last example. No, second to the last, I mean. So limit of 2 all over x squared minus 4 to the power of 4 as r approaches to negative 1 from the left. So I'm really very sorry for this. This is not r. It's equal to s. Okay, so this should be s, right? So how about this? If ever we'll be analyzing, it's negative 1 from the left. However, if you'll be looking at it, if you substitute, it will not make the denominator 0. So that is why you will apply the usual limit solving. So maybe you're wondering why examples like this were included in infinite limits. It is because by the end of the day, if ever you will be solving some admission exams, or perhaps periodical exam like long quizzes, it will not be always that, it will not always be like every item will be all infinite limits. Every item will be all limits at infinity. You need to first analyze the problem. If this problem is for limits at infinity, or this problem is for infinite limits, or if this problem is for factoring or whatever, or whichever it will be under with. So that is why you need to be very mindful. So to continue, um, if we simplify this will be 2 all over, so -1 squared, I believe that's equal to 1 minus 4 then squared. And so if we solve further, 1 minus 4 is -3 squared, and -3 squared is equal to 9. So our answer for this is equal to 2 over 9. Okay, so again, this is just a reminder that in solving limits, it's not always infinite limits. There might be some times wherein you just be doing the usual substitution. Okay. So let's proceed to the last example we have here. So limit of 3 over x plus 1 as x approaches to -1. So let's try to do some inspection here. So it is approaching to -1. However, it's a two-sided limits. Okay. Now, if you substitute in the -1 to the denominator, it will be 0. So therefore, there is a greater chance that you will be applying infinite limits. So if we solve this, I believe it will be a lot safer if we break, if we break the two-sided limits into two different one-sided limits. So if you can recall, so this will be limit of 3 over x plus 1 as x approaches to -1 from the right. And the other one will be limit of 3 over x plus 1 as x approaches -1 from the left. So again, if the usual way, I believe the answer for this is really undefined. It's just that we need to make sure to know the value or the answer for each one-sided limits from the right and from the left. So if we solve this, so it is coming from the right. So as mentioned from theorems under infinite limits, if it is coming from the right without any more analyzation, it will be automatically equal to positive infinity. And if you will answer this coming from the left, so we remember that our R, if is even or add. And again, I just want to write it again just for you to remember. If R is even, it will be positive infinity, and if R is odd, it will be negative infinity. So if we solve this, I believe if ever we will be rewriting this, it will be 3 all over x plus 1 to the power of 1 as x approaches -1 from the left. So coming from the left, and R is equal to 1, and it is an odd number. So if it is an odd number, automatically it's equal to negative infinity. So positive infinity and negative infinity, I know these are also D and E. However, again, this represent increasing numbers and decreasing numbers. So positive infinity and negative infinity, therefore the answer for this is actually equal to D and A, or does not exist, because basically they're not equal, or the representation or the symbol are not the same. So that's why we conclude that the answer for this is equal to does not exist. All right, so that's the last example under that theorem provided earlier. Now this time there are some there is still another theorem under infinite limits that we need to familiarize, especially if ever we'll be dealing problems like this. Let me go ahead and show you the theorem. No, so let limit of f of x as x approaches a is equal to c. So assuming that the answer for limit of f of x is equal to c, a constant wherein it's not equal to 0. So any other number, as long as it's not equal to 0. And our limit of g of x as x approaches a is equal to 0. So in this specific theorem, okay, I just want to emphasize we have two functions, f of x and g of x, wherein the value of our f of x is a constant c, saying that c must not be equal to 0. And our second function, g of x, has a value of 0. So what if we are in this format? So what if we solve the value of limit of, okay, so it's in rational form, the first function f of x over the second function g of x as x approaches to a, it will be equal to positive infinity if given these two conditions. So what are these two conditions, sir? So these two conditions are if, please take note of this one first. So let's focus on the one I boxed. So C greater than 0. So if you solve for the value of the numerator, and again, granted that it's a constant, but as mentioned, it must not be equal to 0. So assuming that we solve it and the value is greater than 0, and our g of x, okay, we know that g of x is 0. However, the values of our g of x is approaching to 0 from the right, then technically, everyone, the answer for that is positive infinity. The same thing here. For example, if we have c, so if we try to solve the value for the numerator f of x, and c is lesser than 0, so numbers lesser than 0, like the negative numbers, and g of x is approaching to 0 from the left, still the answer is equal to positive infinity. Now, what's the other theorem, sir, under that? So the other one is this. It will be negative infinity if following these two conditions. So let's try to analyze first the first condition on the second theorem. So it will be negative infinity if the value of our c, or the value of our f of x when substituted from a, is greater than 0. However, our g of x, the denominator, which is I know 0, however, it is approaching to 0 from the left. So the answer for that is equal to negative infinity. On the other hand, also c lesser than 0, so meaning numbers lesser than 0, negative numbers, and g of x this time is approaching to 0 coming from the right. So therefore, everyone, the answer for that is negative infinity. So again, I just want to emphasize, what we'll be doing here is we need to solve the value of our f of x from x approaching a. And after solving that, we need to analyze whether that value is greater than 0 or lesser than 0. Afterwards, let's try to analyze our denominator, because the denominator will be equal to 0. And let's try to analyze if our g of x is approaching to 0 from the right or 0 from the left. All right, so let's try to have some examples here. All right, so this will be the first example on the second set of theorem. So here, limit of 3 plus 5y all over 1 minus 2y as y approaches to 1 from the right. So if you will be analyzing it, if we substitute 1/2 to the denominator, 1 minus, so if ever I'll be solving it, 1 minus 2 times 1/2, so technically it will be equal to 0. So it satisfy the condition from the theorem that our g of x is equal to 0. Now, let's try to analyze the second one, the denominator, the numerator, I'm sorry. So it is 3 plus 5y. And if you substitute, that will be 3 plus 5 times 1/2. And I believe so it will be 5 over 2. And 3 is 6 over 2 plus 5 over 2. So it is 11 over 2. So 11 over 2. So it is a positive number. So we say that c is equal to 11 over 2. C, which is the value of the limit of the numerator, and it is greater than 0, right? Because it's a positive number, so it is greater than 0. So C is 11 over 2 greater than 0, and g of x is equal to 0, approaching from the right, okay, from the right. So positive greater than 0 from the right. So our answer here is equal to positive infinity. Because if you can recall on the first condition, on the first number under that specific theorem, if c is greater than 0 and our g of x is approaching to 0 from the right. So here, it's 0 and also approaching from the right. So that is why it satisfies the first condition under the first theorem, that is equal to positive infinity. So that's how you do it when you will be solving infinite limits like this. All right, so let's have the second example, which is this. Limit of 5y all over y minus 3 as y approaches to 3 from the left. So if we solve this, again, the same thing, we solve the numerator. So the value of numerator is 5y, and if you solve that, it's 5 times 3 from the left, and the answer is 15. So 15, I believe, which is c, right? 15 is equal to c, the value of the limits of our numerator, and that is greater than 0. So c greater than 0, And so, yeah, you need to take note of this. And let's proceed to the denominator. The denominator is, if we substitute y minus 3, and it will be 3 from the left minus 3, and it is equal to 0. So our g of x is equal to 0. However, if you notice, it's approaching 3 from the left, so from the left, and greater than 0. So therefore, from the theorem we have earlier, it is equal to negative infinity. So the answer for example number 2 is equal to negative infinity, meaning the values of our y decreases indefinitely. I'm sorry, the value of the function decreases indefinitely as our y approaching to 3 from the left. So that's what we meant by negative infinity. So do not be confused, okay, that the answers for all of these is actually does not exist. It is just that we need to find a representation wherein how your values of those function behave when it is approaching to 3 from the left. So that's why it is decided that for this function it is approaching to, or the answer is negative infinity, again meaning the value of the function as y approaches to 3 from the left decreases indefinitely. All right, so let's proceed to another example, which is limit of 2x minus 3 all over 1 minus x as x approaches 1 from the left. So let's solve. So let's solve for the numerator. Oh, sorry. So let's solve for the numerator. We have 2x minus 3. Oh, so if 2x minus 3, so you substitute 2 times 1 from the left minus 3. And if you simplify that, it will be 2 times 1, which is 2 minus 3. And here we go. We have negative 1 answer. So negative 1 is our C, and negative 1 is lesser than 0. And then after that, let's solve for 1 minus x, and it will be 1. Oh, sorry. So 1 minus x. So therefore, it will be 1 minus 1 from the left, and that is equal to 0. So 0, so our g of x is equal to 0, and we are approaching 1 from the left, so it's from the left and lesser than 0, so the answer for this is equal to positive infinity. All right, so how did I know that it's positive infinity? Again, let's go back to the theorem that our c is lesser than 0, and we are approaching 1 from the left because our g of x is equal to 0. Okay, let's proceed to another example here. So we have limit of 1 minus 2x all over x plus 7 as x approaches negative 7 from the right. So the same thing on the same drill actually, guys, we substitute, we solve, so we replace the value of x with a. So it's negative 7 from the right, and then that will be 1 minus, so minus 2 times negative 7, I believe it will be positive 14, right? I think you'll agree with that. And when you add 1 and 14, the answer is 15. So this is the value of our C. And 15 is, I believe, greater than 0. So yeah, C is greater than 0. Now let's proceed to our denominator. Denominator x plus 7. So negative 7 from the right plus 7. And I believe it's equal to 0. So G of x is equal to 0, and it is approaching to negative 7 from the right. So from the right and greater than 0. So therefore, everyone, the answer for this is equal to positive infinity. Later on, I'll teach you a technique on how will you be able to easily remember these things. Okay? So, but this is how we solve this specific example. All right, so let's proceed to, no, basically we're done. So let me go ahead and show you my way of easily thinking and easily analyzing when can we say it's positive infinity and negative infinity. You can do this one when you will be um, solving more examples about infinite limits with problems like this. So this is just how I see it. So if it is c greater than 0, understandable that the values of our c is positive, right? So if it's positive and it is approaching positive or from the right, so technically, guys, positive and positive, it's positive infinity. The same thing here. If c is lesser than 0, So if c is less than 0, it's understandable that we are concerning with negative values, right? So negative values and approaching from the left. So if you can, like the usual multiplication, when you have negative and negative, the answer for that still is positive infinity. That's why I can easily analyze whether it's positive infinity or negative infinity. Now let's go back to, or I mean, let's proceed to negative infinity. Here, c greater than 0. So c greater than 0, those numbers are positive numbers. And coming from the left, so negative. So z plus positive and negative, that's why it's negative infinity. And here, c is lesser than 0. That means that we are considering values that are with having nature of negative numbers, so negative, and coming from the right, positive. So negative and positive, we were able to get a negative infinity answer. So that's how I usually remember, like the usual multiplication. If you multiply two positive numbers, it's positive. If you multiply two negative numbers, it's positive. And if you multiply two opposing nature or two opposing signs like positive and negative, it is equal to negative. So that's how that's my technique and how to remember um, with concepts like this. So basically, that's it. That's actually it for infinite limits. Thank you for listening and enjoy the rest of your day. Bye bye.